Okay, so again, there's two types of extrema, absolute and relative extrema. Today we're going to focus in on the absolute extrema and how to use calculus to find the absolute extrema over an interval. And then next week in 3.3 we'll talk about how to find the relative extrema using something called the first derivative test. So we're going to switch gears just a little bit from what we were talking about in chapter 2, or at the end of chapter 2 we were talking about related rates. In this chapter we're going to be talking mainly about extrema, but we're going to use what we learned in chapter 2 to help us find those extrema. So you'll still need to know how to do chain rule, product rule, quotient rule. All of those rules that you learned in chapter 2 are going to follow us really throughout the rest of the year. So if you look at your guided notes that I've given you, again you'll see the two types of extrema, absolute max and min versus relative max and min. There are other terms that some textbooks use. Instead of the word absolute, some textbooks call it global extrema. So that's just another term that means absolute extrema. And then instead of relative extrema, some textbooks call it local extrema. Those terms can be used interchangeably, and really just depending on the textbook, some textbooks call it global, others call it absolute. Some textbooks say local extrema, other textbooks say relative, but they can be used interchangeably. Now, however, absolute extrema are different from relative extrema in most cases by definition. Absolute extrema just means for the absolute max, the highest y value on the graph. What is the highest y value on the graph? For absolute minimum, what is the lowest y value on the graph? That's absolute extrema. Local extrema, you can think of, if you think about a graph, you can think about a point up on top of a hill or a point down in a valley. In other words, a local max is where the graph changes from increasing to decreasing, and a local min is where the graph changes from decreasing to increasing. So it actually has to change slope to be considered a local extrema. So over here in the corner where you see this blank space, I'm just going to draw you a few examples of graphs, and we're going to label the extrema on these graphs. So my first graph, up in the top right hand corner, it's going to look like this. That looks like this. So I'll give you a chance to just sketch. It doesn't have to be perfect. Just sketch those three graphs on your paper, and then we're going to label the extrema on those graphs, just to give you an idea in your head, kind of the difference between absolute extrema versus local extrema. Because like I said, in this section we're focusing in on how to find absolute extrema using calculus, but next week on Tuesday we'll learn how to find local extrema using calculus. So let's look at the first graph in the top right hand corner. If we're talking about absolute extrema, absolute max or absolute min, there is an absolute maximum value. Remember, absolute max just means the highest y value on the graph. That would occur at this point here. This is what I would call my absolute max. What can you tell me about the absolute minimum? It's going to negative, the graph is going to negative infinity. I agree with that. But as far as an absolute minimum is concerned, there is not one. So if the graph is going to negative infinity, that just means there is no lowest y value. Because remember, positive and negative infinity are not numbers. That just means positive infinity means the numbers keep getting higher, so there is no highest number. And negative infinity means the numbers just keep getting lower, so there is no lowest number. So for the first graph, there is not an absolute minimum. Let's talk about local extrema. I have 3 total local extrema. Okay? I have two local max and 1 local min. Remember, a local max is when the graph changes slope from positive to negative, or changes from increasing to decreasing. So this point here would be considered a local max. Up on top of this, I mentioned hills and valleys. Up on top of this little hill, we have a local max. Where would the other local max be?
Where the absolute.
Yeah, right there where the absolute max is. So this point and this point would both be considered local max values. And then the local minimum occurs where the slope changes from negative to positive, or in other words, the graph changes from decreasing to increasing. So I only have one of those. I do have a local minimum, it occurs here. And I'm just labeling those. Okay, let's look at this second graph. What can you tell me about the absolute maximum? It does not have an absolute maximum because the graph is going to positive infinity. Does it have an absolute minimum?
Yes.
It sure does. It has an absolute minimum right down here. I'm going to label that absolute min. How many local extrema do I have for this graph?
3.
I still have 3, but this time I have 2 local mins and 1 local max. Good. So this is going to be my local max here. Local max. And both of these points are considered local min values. Remember, to be a local extrema, the graph has to change slope at that point. The graph has to change slope at that point. All right, let's look at the last graph. Notice that notice the domain of this function, by the way. On the left-hand side, it's going to negative infinity, but on the right-hand side, I stop at a point. This graph does not continue on in the positive direction. So for this one, where would the absolute max occur? At that point, that's right, at that point. My absolute max is here. Absolute max, let's just label it. Absolute minimum? It does not have an absolute minimum. How many local extrema do I have? I have 2. I have 1 local max and 1 local min. So I'm going to just draw an arrow from the word local max to this one, and an arrow from local min to this one here. So that's my local max because it changes from increasing to decreasing, and this is my local min because it changes from decreasing to increasing. Notice that for an absolute extrema, it doesn't have to change slope. It's okay if it does, but it doesn't have to change slope to be considered an absolute extrema. But it does have to change slope to be considered local extrema. Does everybody have a clear picture in their mind the difference between absolute and local extrema? Or any questions, I should probably say, about that? Okay. Now, for the graphs that I have given you as examples, for especially the first 2 graphs, those are over an open interval from negative infinity to positive infinity. Today what we're going to be doing is finding extrema on a closed interval. So I might say, okay, look at this graph and tell me what the absolute extrema are when x is in between 0 and 5. So if I'm only looking between 0 and 5, I would not include this extrema over here, but I would only include absolute extrema on that interval. So keep that in mind. In the middle of the page, you'll see something called the extreme value theorem. Now, towards the end of the year, we will have a day devoted just to theorems where we'll talk about them more in detail. But I did want to add this one in your notes. It says if f is continuous on a closed interval, then it has to have both an absolute max and an absolute min on that interval. That's theorem 3.1 from your textbook called the extreme value theorem. We'll talk much more about that later, but for now we need to discuss something called critical numbers. So here in the empty space we're going to write some steps for finding the critical numbers of f. So critical numbers are found by, first of all, you're going to find f prime. So find the derivative. You might have to use product rule, quotient rule, chain rule, or just plain old power rule. Then you're going to set f prime equal to 0 and solve. Then you're going to find values where f is not differentiable. That simply means that f prime does not exist at that particular x value. Find values where f is not differentiable, and then only choose values on the interval that you are given. So, why do we need critical numbers? We need critical numbers so that we can find absolute extrema. We need to be able to identify the critical numbers of a function. So look at the bottom. I went ahead and typed these guidelines in for you. The guidelines for finding, and make a little note here, this is for finding absolute extrema. I want to just clarify that this is for finding absolute extrema on a closed interval. The first thing you do is find the critical numbers of f on the interval that they give you. Then evaluate the original function f at each critical number. Then evaluate f at each endpoint. The least of those values is a minimum. The greatest of those values is a maximum. So let's try an actual example now that we have the steps. If you'll flip over to the next page for me, or to the back of your page, we're going to locate the absolute extrema of the function on the closed intervals. So notice, number 1, f of x equals x squared plus 2x minus 4 on the interval -1 to 1. Now remember, these are x values, -1 to +1 on the x-axis. And so if we follow our guidelines, the first thing we have to do is to find the critical numbers. And how do we find the critical numbers again? Well, the first thing you do is find the derivative and set it equal to 0. So what is the derivative of x squared plus 2x minus 4?
2x.
2x plus 2 minus 0.
2x plus 2 minus 0. And I'm just going to write 2x plus 2. And so find the first derivative and set it equal to 0. Then you're going to solve for x. And I get x equals -1 for my critical number. Now what you're going to do is you're going to test, as long as the critical number is in your interval, and it is, you're going to test the critical number and the endpoints into the original function. So that means over here to the side, I'm going to find f of -1 and f of +1, since -1 is actually one of my endpoints. So if you substitute in to the original function, you get -1 squared plus 2 times -1 minus 4. Well, that's going to be 1 minus 2, which is -1 minus 4, which is -5 for f of -1. And for f of +1, you substitute in 1 squared plus 2 times 1 minus 4, and you get -1. So, now, the least of the values, look at -5 and -1, the smallest value is telling you your absolute minimum, and the largest value is telling your absolute maximum. So, I have an absolute min where? The absolute min is -5. What's the order pair? -1, -5 is my absolute minimum. And then I have an absolute max at +1, -1. Okay, now if you think about the graph here, just so you can visualize, let me get my calculator out. Just so you can kind of visualize what we just found. If you type in the original function, x squared plus 2x minus 4, and we graph it, we know it's a parabola that opens up. This is what my graph looks like. Now, if you think about the absolute extrema over the entire interval, you know that it has one absolute minimum, but it doesn't have an absolute maximum over the entire interval. But these are on restricted intervals, so we're only looking at the piece of the graph from x equals -1 to x equals +1. That's all we care about, okay? So if we were to graph this function on the interval -1 to +1, then it would look like this. It would have a closed circle down here at -1 and a closed circle up here at +1. So this graph is what we're finding the absolute min and the absolute max of. Just that piece of the graph from -1 to +1. So hopefully you can see the absolute minimum occurs down here at -1, -5, and the absolute max occurs here at +1, +1. Does everybody understand that? We're only looking on a closed interval for these absolute extrema. All right, let's look at number 2. Let's try to find the absolute extrema for number 2. So the first thing you do is you take the derivative, f prime, and set it equal to 0. What is the derivative of number 2, Mason?
12x to the third minus 12x squared.
Great. 12x to the third minus 12x squared. After you find the derivative, set it equal to 0 and solve for x. Now, if I want to solve this for x, what do you think we need to do to get x by itself here?
Factor it out.
Yes, factor. Good. Factor out the GCF. What is the GCF?
12x squared.
12x squared. And you're left with x minus 1. Set each factor equal to 0 and solve for x. So x equals 0 and x equals 1. Now, the next thing I need to check is to make sure those numbers are on my interval. I have to make sure those numbers are on my interval. Is 0 in between -1 and +2?
Yes.
Yes. And is 1 in between -1 and +2?
Yes.
Yes. So that means I test those as well. If I had come up with like 0 and 3, I would test 0, but I would not test 3. Okay, so you always have to check to make sure your critical numbers are actually in the interval. And so now I'm going to test 0. I'm going to test 1. And what else do I test?
-1 and 2.
-1 and 2. So this time I have 4 numbers to test. And I test them into the original equation. So you test your critical numbers and the endpoints every time. The critical numbers and the endpoints. Up in number 1, the critical number was an endpoint. That's why we only had 2 things to test. So I'm going to use my calculator to help me out a little bit here. Well, I don't need it for 0, do I? Actually, may not need it for any of it, will I? I'm not going to write it all down, but if you need to remind yourself that we're subbing into the original function, not the derivative. When you sub in 0, you get 0. What about when you sub in 1? -1. And when you substitute in -1, you get 3 times +1 minus a -4. So it's going to be 7. And when you substitute in 2, you get 3 times 16, which is 48, minus 4 times 8, which is 32. 48 minus 32 is 16. And so what is my, or where I should say, is my absolute minimum? At the point 1, -1. And by the way, the absolute minimum is -1. The x just tells you where it occurs. The y value is the actual minimum. So where's the absolute max? At 216. That's right. So you pick the smallest y value for the absolute min and the largest y value for the absolute max. Okay, moving on to number 3. First thing I'm going to do is I'm going to write this as x to the 1/3 power instead of the cube root of x. Then I'm going to take the derivative. So what's the derivative of x to the 1/3 power, Robbie?
1/3 x to the -2/3.
Good. 1/3 x to the -2/3. And now before I set that equal to 0, I'm actually going to clean it up a little bit and say 1/3x to the 2/3. I'm going to move that x to the -2/3 to the bottom with the 3. And then I'm going to set it equal to 0. Now, to find the critical numbers of a fraction, what you have to do is you have to find the x-intercepts, but you also have to find where the derivative is undefined. So for any fraction, any derivative that is a fraction, the rule is to set the numerator equal to 0 to find the x-intercepts, and set the denominator equal to 0 to figure out where it's undefined. Okay? So if we set the numerator equal to 0, we're not going to get anywhere because we don't have an x for this problem. But if we set the denominator equal to 0, this is going to tell me where the function, where the derivative of the function is undefined. So remember earlier I mentioned figure out where f is not differentiable. It's not differentiable if the derivative is undefined. So I set this equal to 0 and solve for x. How do you get rid of a 2/3 power? Well, the easy way is just to raise it to the 3/2 power. Raise it to the reciprocal power. So you're going to raise it to the 3/2 power. Now this one's pretty trivial because 0 to any power is just going to be 0. But I want you to know that in case you had a number on the other side. So to get rid of a fractional exponent, you just raise it to the reciprocal power. Because remember, when you raise a power to a power, you multiply exponents from Algebra 1. And 2/3 times 3/2 is just 1. And then 0 to the 3/2 means the square root of 0 cubed. Well, 0 cubed is just 0, and the square root of 0 is just 0. So, is 0 in my interval? Yes, it is. So, I test f of 0, and what else? F of -1 and f of +1. And I test them where? In the original. When you test 0, what do you get, Elizabeth?
0.
Good. And when you test -1, what do you get, Jordan?
Positive 1. Well, no, it would be -1, so.
It would still be -1, you're right. And when you test +1, Angel? 1. Good. So we're testing them into the original function. Remember, cube root of 0 is 0, cube root of -1 is -1, and cube root of 1 is just 1. So that means I have an absolute max where? Well, let's do absolute min since that's the one we've been doing first. -1, -1, and where is my absolute max? 1, 1.
So,
Yes.
so what does, for your numerator, when you set that equal to 0, what does that tell you again?
So that tells you that that actually tells you where the derivative equals 0. That's the x-intercept of the fraction. Because 0 divided by anything is 0. So a quick way to find where a fraction is equal to 0 is just to take the numerator and set it equal to 0. So every time you get a derivative that is a fraction, what you're going to do is you're going to take the numerator, set it equal to 0, and then the denominator and set it equal to 0 separately. The numerator equal to 0 gives you the x-intercept, or the 0 of the function, and the denominator equal to 0 tells you where the original function is not differentiable. Because remember, when you divide by 0, that causes it to be undefined. So if the derivative is undefined, the original function is not differentiable. Any other questions before we look at example 4? What time do we get out of here? What is it? Is it 40? It is 40, isn't it? And then we're just going to our video locations, is that right? Okay. Okay, let's try to get through example 4. And so on example 4, we're doing the same thing, absolute extrema. So what do we need to find the derivative? We got to do quotient rule this time. So we do low, d high, minus high, d low, over low, low. And then we're going to simplify the numerator. So t minus 2 minus t over t minus 2 squared. And so we get -2 over t minus 2 squared. So again, we have a derivative that is a fraction, which means we have to set the numerator equal to 0 and the denominator equal to 0. Okay, so if we set the numerator equal to 0, we don't have a variable to solve for in this case either. If we set the denominator equal to 0, how do we solve that? Square root both sides. We get plus or minus 0, but we all know positive 0, plus 0, and minus 0 are the same thing. And add 2 to both sides, t equals 2. Do I test 2?
No.
Why not?
It's not in there.
It's not in the interval. That's the only reason I don't test 2 is because it's not in the interval. Excuse me. All right, so now, what should I test?
3 and 5.
3 and 5. So I'm going to say, excuse me again. I'm going to do h of 3 and h of 5. So if I put 3 in, what do I get, Justin?
You get 3.
3, good. And if I put 5 in, what do I get, Kaylee?
5 over 3.
Good, 5 over 3. So where would my absolute min occur? Nick?
Would it be 5/3?
You got it, 5/5. And Evan, what does that mean about my absolute max? Or where would it be?
Would it be 5/3?
Absolute max is just gonna be the other point that we have. So we just pick the largest y value. So it's gonna be at 3, there you go. It's gonna be at 3. So again, to find the absolute min and the absolute max, you just look at your y values. 5/3 is just like 1 2/3, so it's the smallest number. 1 2/3 is smaller than 3. So that's why I chose that for the absolute min. And then the absolute max has to be 3, which is at the point 3. Okay. Let's see how much we can do of number 5. Sure. I have an assignment for this section and I'll just post it on Emoto, okay? Sure. Okay, number 5 says a retailer has determined that the cost C of ordering and storing X units of a certain product is the function C. Notice that it gives you X is in between 1 and 300. By the way, this is an interval too. This just means bracket 1, 300, just like we've been doing. Just another way to write that, okay? It says the delivery truck can bring at most 300 units per order. Find the order size that will minimize cost. What's it looking for?
Absolute min.
Absolute min on that interval, right? Could the cost be decreased if the truck were replaced with one that could bring at most 400 units? Well, let's answer the absolute min first. Let's answer the absolute min first. So we need to take the derivative of C equals 2x plus 300,000 x to the negative 1. I wrote it that way so that I could just use power rule and not have to use quotient rule. So that means C prime is just 2 minus 300,000 x to the negative 2. Good. Set that equal to 0. And then 2 minus 300,000 over x squared. Equals 0. Can you tell me where the first derivative does not exist just by looking at it here? It does not exist at 0, right? So I've got to include 0 if it's in my interval. Is it in my interval? It's not in my interval. But if it were in my interval, I would have to include it because that's where the derivative does not exist. Always think about that. What I like to do if I get a fraction, I like to go ahead and get a common denominator and just write it as 2x squared minus 300,000 over x squared so that I can set my numerator equal to 0 and my denominator equal to 0. But we already talked about the fact that x equals 0 is not in our interval. What about this over here? Well, if we solve this one, we get x squared equals 150,000. So x equals the square root of 150,000. We only want the positive square root because we're talking about number of units. A negative square root wouldn't be in our interval. Is the square root of 150,000 in our interval? Well, the square root of 150,000 is approximately 387. It's not in our interval either. So what do we test? C of 1 and C of 300. Okay, so if you do, I know I'm running out of time, so if you do C of 1, you get 300,002, and if you do C of 3, you get 1,600. Or C of 300, sorry. C of 300, you get 1,600. So which order minimizes cost? Of course, the 300. All right, that's the absolute minimum. Now let's talk about the second part of the question. If I raised my interval to 400, if I increased, if I changed the truck so that I got a bigger truck that would hold 400 units, would that change my answer? Okay, how do we know? What would we have to test? Now we got to test C of square root of 150,000. And by the way, you don't want to use 387. You want to use the exact value. So you want to test square root of 150,000. Because on that AP exam, if you use a rounded answer to get a rounded answer, they're not going to give you credit. You have to use the exact answer to get your rounded answer to 3 decimal places. So, for sake of time, I'm going to tell you what this answer is. It's 1549.193. Now tell me what the order size would be to minimize the cost. About 387. And on the AP exam, they would tell you to round that to the nearest whole number because we're talking about number of units or, yeah. Everybody okay with that?
Yes.
Well, let me give you your assignment for this section. It's going to be on page 165. I want you to do 11 through 14. Then I want you to do 17 through 23. And 25 and 27 over the weekend. 11 through 14.